Tonight, we're going to explore something that sounds simple, but is actually one of the strangest discoveries in all of astronomy: a galaxy with no stars. You've probably seen galaxies in pictures, bright spirals, glowing clusters full of light. Scientists talk about them constantly when describing the universe. But here's what most people don't realize. When astronomers actually found a galaxy with almost no stars, when you try to imagine a place that is mostly empty, yet still exists, it changes how you see the cosmos. This is not just a dark patch in space. It's a structure so unusual that it challenges our ideas about how galaxies form and evolve. And by the end of this journey, you're going to understand exactly why this discovery matters and why nothing like it had been seen before. Before we go any further, if you enjoy deep, careful explorations like this, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. The universe stretches far beyond the limits of what the human eye can see. Night after night, the sky appears dotted with tiny points of light, each one a star, a burning sphere of gas shining across unfathomable distances. These points gather into shapes and patterns, the familiar constellations that have guided humans for millennia. Beyond these constellations, beyond the veil of what seems visible, there exists a vast expanse that is harder to perceive, a darkness filled with matter that does not shine. For centuries, astronomers studied the stars, counting them, measuring their brightness, and mapping their positions. They assumed that galaxies, the immense collections of stars, were defined by these points of light, that a galaxy without stars would be invisible, unnoticeable, and perhaps impossible. Yet the universe does not always conform to human expectation. Some structures are hidden, their mass invisible, their presence only suggested by the way they affect the objects around them. The idea that a galaxy could exist without stars challenged the most basic assumptions of astronomy. Galaxies are usually considered bright. A spiral galaxy glows with countless young stars, scattered across arms that wind outward from a central bulge. Elliptical galaxies appear smoother and softer, their older stars giving off a steady, muted light. Even small, irregular galaxies display stars of various ages, colors, and sizes, a testament to the ongoing cycles of formation and decay. Within these galaxies, clouds of gas and dust move slowly, collapsing under gravity to create new stars, while other stars die, leaving behind compact remnants such as white dwarfs, neutron stars, or black holes. Each galaxy carries a story of creation, destruction, and renewal, visible in the light it emits. To imagine a galaxy without any stars is to imagine a place where that cycle has been halted, where the processes that give rise to light have failed or been interrupted. Yet, astronomers have long suspected that not all galaxies need to shine. Dark matter, the invisible substance that outweighs ordinary matter in the universe, exerts a gravitational pull that binds galaxies together. While dark matter cannot be seen, its influence is evident in the way stars and gas clouds move, in the shapes of galaxy clusters, and in the bending of light from distant sources. This unseen framework suggests the possibility that some galaxies could exist primarily in the dark. They might contain gas, dust, and dark matter, yet emit little to no light, because star formation has not occurred. These hypothetical objects are sometimes called dark galaxies, but confirming their existence is not simple. Detecting them requires looking not for light, but for the subtle signs of mass and motion that reveal something massive but invisible. The scale of the universe makes such discoveries both difficult and profound. The nearest galaxy clusters lie millions of light years away, and the signals that reach Earth are faint and distorted. Every photon of light captured by a telescope tells a story of its journey, passing through space filled with hydrogen, dust, and cosmic radiation. Observing the invisible requires different strategies. Radio waves can detect cold hydrogen gas, while gravitational effects show the influence of mass on nearby objects. For centuries, these methods were limited by technology, but advances in instrumentation now allow astronomers to explore the dark side of the cosmos with greater precision. Surveys that once focused on bright galaxies now scan the sky for the subtle signature of hydrogen gas clouds, searching for the silent footprints of objects that contain matter but not stars. The notion of a starless galaxy touches the heart of cosmic understanding. It forces a reconsideration of what defines a galaxy, not merely as a collection of stars, but as a gravitationally bound structure that can exist in the absence of visible light. These objects demonstrate that the universe holds more diversity than human senses can immediately detect. A starless galaxy challenges the assumption that light is the primary marker of matter, that seeing is the same as knowing. Instead, astronomers must interpret faint signals, trace the movement of gas, and weigh the invisible mass that hints at something profound hidden in the dark. Every discovery of this kind reshapes the map of the universe, extending knowledge into realms that are not illuminated by stars, but are no less real. Even without stars, a galaxy can have structure and mass. Observations of hydrogen emissions allow astronomers to map the distribution of gas, revealing regions of density and movement. Radio telescopes, tuned to specific wavelengths, detect clouds of hydrogen that may be spread across tens of thousands of light years. The motion of this gas, its rotation and turbulence, provides clues to the gravitational forces at work, confirming that mass exists where no stars shine. These measurements show that the galaxy is held together, not by visible matter, but by an underlying gravitational framework dominated by dark matter. In this sense, the galaxy is no less a complete object than any luminous spiral or elliptical. Its invisibility is not absence, but a different mode of presence, subtle and demanding careful observation to understand. The discovery of such a galaxy begins with careful observation, patience, and an openness to surprise. Telescopes sweep the sky systematically, recording the faint glow of hydrogen, the slight bending of light from more distant sources, and the motions of nearby objects. Astronomers analyze this data, searching for patterns that do not correspond to known galaxies. A region may show a cloud of gas moving as though it were part of a gravitational system, yet no stars are visible. These signals, weak and elusive, must be confirmed through repeated observation and careful modeling. Once verified, the object is recognized as a galaxy without stars, a hidden presence in the vast cosmic landscape. Its discovery is both an achievement of technology and a triumph of careful scientific reasoning. The implications of finding a starless galaxy extend beyond the object itself. It suggests that the processes governing star formation are not universal, that environmental factors can prevent stars from igniting even in the presence of ample gas. Collisions with other galaxies, stripping by hot intergalactic plasma, or intrinsic properties of the dark matter halo, may halt the cycle of star birth. Studying these galaxies provides insight into the conditions required for stars to form and thrive. By understanding what stops star formation, astronomers gain perspective on why some galaxies shine while others remain hidden in darkness. In this sense, a starless galaxy becomes a laboratory for the physics of matter, gravity, and cosmic evolution. Observing the universe beyond the visible light spectrum has revealed a richness once unimagined. X-rays, infrared radiation, and radio waves open windows into regions of the cosmos where stars are faint or absent. In these ranges, the presence of gas and dark matter becomes evident. Astronomers now routinely combine multiple observational methods to detect objects that are invisible to the human eye. A starless galaxy, detected through the 21-centimeter emission of hydrogen, shows up as a ghostly silhouette on a radio map. Its mass and shape are inferred from the motions of gas, revealing a hidden structure that would otherwise remain unknown. This multi-wavelength approach transforms the sky from a simple tapestry of points of light into a complex, layered map of both visible and invisible matter. The universe is more intricate than stars alone can reveal. Each new discovery of a starless galaxy adds a piece to the puzzle, demonstrating that galaxies are more than the sum of their visible parts. They are structures governed by gravity, shaped by matter, both seen and unseen, and capable of existing even in complete darkness. This understanding reshapes the way astronomers conceptualize the cosmos, moving beyond the human reliance on light and embracing a more complete picture. By studying these hidden galaxies, scientists probe the limits of observation, test models of formation, and explore the subtle dance between matter, energy, and gravity that governs all structures in the universe. Each starless galaxy is a reminder that the cosmos is not defined by what we can see, but by what exists, waiting for careful observation to reveal it. In this vast, dark expanse, the discovery of a galaxy with no stars is not just an oddity. It is evidence of the unseen forces at work in shaping the universe. It teaches that light is only one measure of existence and that matter can be organized and bound even when invisible. For astronomers, it is both a challenge and an opportunity, a chance to study the building blocks of galaxies in a state unilluminated, to explore the role of dark matter and gas in isolation, and to expand our understanding of how galaxies form and evolve. It invites the imagination not to invent stories, but to extend observation, reasoning, and measurement into realms of reality that remain hidden from simple sight. In this sense, the starless galaxy is a quiet revelation, a testament to the universe's richness, complexity, and capacity to surprise even the most experienced observers. The first sign of something unusual appeared in data collected by one of the large sky surveys. Astronomers were scanning the heavens for hydrogen gas, mapping its presence across nearby regions of space. These surveys, conducted with powerful radio telescopes, detect the faint emission from neutral hydrogen at a wavelength of 21 centimeters. Most of the signals corresponded to known galaxies, their positions matching what had already been catalogued in optical surveys. But in one region, the instruments picked up a cloud of hydrogen moving in a coherent way, suggesting it was bound together by gravity. No corresponding light from stars appeared in images from optical telescopes. At first, this anomaly was treated with caution. Instruments occasionally record noise, and data can be misleading. Astronomers cross-checked observations using different telescopes to confirm the signal. Each confirmation reinforced the sense that they had detected something real, something unlike the galaxies they had studied for decades. The initial measurements were made with the radio dishes of a large array, sensitive enough to detect faint gas across millions of light years. These instruments allow astronomers to map the motion of hydrogen within galaxies, revealing rotation patterns and mass distribution. When the cloud in question was examined, it showed clear signs of rotation, a hallmark of gravitational binding. The velocities of the gas suggested a mass comparable to small galaxies, yet the optical images showed no stars, No light from hot gas, nothing that would indicate the presence of a typical stellar population. The absence of light was puzzling. For every galaxy known at the time, stars produced most of the visible signal. This object seemed to defy that rule, existing as a coherent structure without a single shining star. Once the discovery was confirmed, the team involved began to share the data with colleagues. The reaction was cautious curiosity, mixed with skepticism. The idea that a galaxy could exist without stars had been suggested theoretically, but this was the first time evidence pointed directly to its reality. Some astronomers questioned whether the hydrogen cloud might be part of a faint, unseen galaxy, or debris from interactions between other galaxies. Others wondered if the measurements were influenced by noise or calibration errors. Peer review and independent verification were essential. The scientific method demanded repeated observation, comparison of instruments, and careful modeling to ensure the finding was robust. The debate was rigorous and precise, focused not on speculation but on data and methodology. Over weeks and months, additional observations strengthened the case. Telescopes in different parts of the world scanned the same region, confirming the rotational motion of the hydrogen. Spectroscopic analysis provided details about the gas temperature, density, and velocity, all consistent with a galaxy-sized object. Models of gas dynamics matched the observed behavior, reinforcing the interpretation that this was a galaxy held together by gravity but lacking stars. Each new dataset reduced uncertainty, gradually transforming what had been a curious anomaly into a recognized member of a new category of galaxies. The process highlighted how discovery in astronomy is rarely instantaneous. It is careful, patient work, involving repeated measurements and verification, building confidence slowly from faint signals across the cosmos. The instruments that made this possible were the culmination of decades of development. Radio arrays can detect emissions from neutral hydrogen over millions of light years, translating these faint signals into maps of gas distribution and motion. Optical telescopes, meanwhile, provide images of stars, enabling cross-checks for the presence or absence of light. Together, these tools allow astronomers to explore both the visible and invisible components of galaxies. The synergy between different methods is crucial when studying objects that challenge conventional definitions. A starless galaxy cannot be seen with a traditional telescope alone. Its existence is inferred from gas behavior, from gravitational signatures, and from meticulous analysis of data collected over time. The location of the object within its cosmic neighborhood also offered clues. It was found in a region where other galaxies cluster, where interactions between massive objects are common. In such environments, gravitational forces, tidal effects, and the movement of hot intergalactic gas can strip material from galaxies, potentially suppressing star formation. The presence of a starless galaxy in this context suggested that its history might involve processes that prevented stars from igniting. Perhaps gas had been removed or heated early in its life, making it difficult for dense clouds to collapse. Understanding the surroundings helped astronomers begin to construct a narrative for the galaxy's formation, even in the absence of visible stars. The discovery was documented carefully, with detailed reports describing the observations, the instrumentation, and the methods used to eliminate error. Data tables, spectral plots, and radio maps were analyzed to ensure the interpretation was sound. These documents became a reference point for the astronomical community, allowing independent teams to review the work, attempt to reproduce the findings, and consider the broader implications. This transparency is a cornerstone of scientific discovery. It ensures that unusual claims, especially those that challenge existing knowledge, are subjected to rigorous scrutiny before they are widely accepted. As the evidence accumulated, the galaxy attracted the attention of theorists. Models of galaxy formation were revisited, considering scenarios in which gas could assemble into a gravitationally bound structure without triggering star formation. Theories involving high dark matter content, environmental stripping, or early heating of the gas were evaluated against the observational data. The interplay between observation and theory became central, illustrating how a single discovery can prompt a re-examination of established understanding. In this way, the starless galaxy was not just an object to observe, but a phenomenon that could refine the principles of astrophysics. Publications followed, describing the discovery in journals and conferences. Images, spectra, and velocity maps were presented to the broader scientific community, accompanied by careful explanations of methodology. The narrative emphasized data over conjecture, evidence over assumption. Each presentation reinforced the unusual nature of the galaxy and encouraged further observation by independent teams. Slowly, the idea that a galaxy could exist without stars moved from skepticism toward acceptance, grounded firmly in repeated verifiable data. It became a subject of fascination not only for professional astronomers, but also for educators, students, and science communicators seeking to explain the unexpected richness of the universe. The discovery of the starless galaxy was a moment of both surprise and opportunity. It demonstrated the limits of reliance on light to identify cosmic structures, showing that careful observation and the use of multiple techniques could reveal hidden regions of the universe. The galaxy became a symbol of the unseen forces shaping the cosmos, and a reminder that the universe still holds objects that challenge basic assumptions. For astronomers, it was both a puzzle and a promise, a chance to study an object that exists purely in the gravitational and gaseous realm, without stars, yet fully present as a coherent galaxy. Its identification marked the beginning of a new chapter in understanding the diversity of galaxies and the complex processes that govern their formation. A galaxy is often defined by the stars it contains, the glowing points of light that mark its shape and size. Spiral arms, bulges, elliptical forms, these are all visible because of the stars within them. Yet, a starless galaxy forces a rethinking of this simple definition. If a galaxy can exist without stars, then its identity must lie in something else: its mass, its structure, and the gravitational forces that hold it together. The presence of gas and dark matter can form a coherent system, bound by gravity, rotating in a way that mirrors the motion of traditional galaxies. The stars, while conspicuous, are not essential to the physical reality of a galaxy. They are markers, yes, but not the foundation. A galaxy without stars demonstrates that the skeleton of a galaxy is invisible, yet fully present, shaped by unseen forces. The invisible framework is largely composed of dark matter. Unlike ordinary matter, dark matter does not emit, absorb, or reflect light. It cannot be seen directly, but its presence is inferred from gravitational effects. In luminous galaxies, the rotation of stars and gas reveals dark matter halos surrounding the visible matter. The mass of these halos often exceeds the mass of all the stars combined, demonstrating that what is visible is only a fraction of the total. In a starless galaxy, dark matter dominates even more conspicuously. The gas, while detectable through radio emissions, represents only a small portion of the total mass. It is the dark matter that binds the system, maintaining the galaxy's cohesion and shaping its overall structure. The unseen halo exerts gravitational pull, dictating the movement of gas and any potential fragments of matter within the galaxy. Comparing starless galaxies with luminous ones highlights both differences and similarities. Luminous galaxies display complex internal structures driven by the presence of stars. Spiral arms, bars, and central bulges emerge from gravitational interactions, angular momentum, and the distribution of visible matter. Stars inject energy into their surroundings through radiation, stellar winds, and supernovae, influencing gas motion and chemistry. In contrast, a starless galaxy lacks these processes. The gas moves under the influence of gravity alone, without stellar feedback. The structure is smoother, simpler, and more uniform, yet the mass and rotation can resemble those of a small spiral or elliptical galaxy. In this way, the starless galaxy is both familiar and alien. It shares the gravitational characteristics of ordinary galaxies, but lacks the visible complexity that stars provide. The distribution of gas within a starless galaxy is a critical feature for understanding its nature. Neutral hydrogen, traced by 21 centimeter radio waves, forms the bulk of the detectable material. The gas is often spread across tens of thousands of light years, forming a diffuse cloud that rotates around the center of mass. Within this cloud, density fluctuations exist, regions where the gas is slightly thicker or thinner. In a luminous galaxy, such fluctuations would often collapse to form stars, but in a starless galaxy, these clouds remain inert. The lack of star formation may indicate that the gas is too warm, too diffuse, or subject to environmental effects that prevent collapse. These properties provide insight into the physics of galaxy formation and the conditions under which stars can or cannot emerge. Dark matter's dominance in these galaxies also reveals its role in shaping cosmic structures. The gravitational pull of dark matter ensures that the gas does not disperse, maintaining a coherent system even in the absence of stars. The halo creates a potential well, a region in which the gas can orbit and rotate steadily. In luminous galaxies, the halo interacts with stars and gas, contributing to the overall dynamics. In starless galaxies, the halo's effects are more apparent because they are unmasked by luminous matter. By studying these systems, astronomers can better understand how dark matter governs the formation and stability of galaxies in the broader universe. Observing the motions of gas provides a direct measurement of dark matter's influence, highlighting its central importance in cosmic structure. Despite lacking stars, a starless galaxy can exhibit motion and rotation patterns similar to those of a traditional galaxy. The gas rotates around the center, following the gravitational potential set by the dark matter halo. Measurements of velocity across the system allow astronomers to calculate the galaxy's mass and distribution of matter. The smooth rotation curves resemble those seen in small spirals, though without the spikes and variations caused by stellar gravity. In this sense, the starless galaxy is a stripped-down version of a luminous galaxy, revealing the underlying physics in its most basic form. Its behavior demonstrates that stars are not required for gravitational coherence, only for light and visible complexity. The chemical composition of the gas in a starless galaxy also differs from that of typical galaxies. Stars create heavy elements during their lifetimes and spread them through supernova explosions, enriching the interstellar medium. In a galaxy without stars, this enrichment does not occur. The gas is more pristine, composed primarily of hydrogen and helium, with few heavier elements. This purity provides a glimpse into conditions similar to those in the early universe, before widespread star formation enriched the cosmos. By examining these unaltered gas clouds, astronomers can study primordial matter in its simplest form, offering a window into the processes that occurred in the first galaxies. Starless galaxies also challenge the ways astronomers categorize galaxies. Traditional classification schemes, based largely on optical appearance, cannot capture objects that emit no visible light. Instead, new methods focus on mass, rotation, gas content, and dark matter distribution. These criteria allow scientists to define galaxies in terms of their physical structure and gravitational cohesion, rather than their luminous properties. In this sense, starless galaxies extend the concept of a galaxy to include objects that exist primarily in darkness, bound and structured, yet invisible except to instruments sensitive to other forms of radiation. The study of starless galaxies also sheds light on galaxy evolution. In luminous galaxies, interactions with neighbors, supernova feedback, and internal dynamics shape the ongoing formation of stars. In starless galaxies, these processes are absent or halted. They represent a branch of galactic development in which the conditions for star formation were never met or were removed early in their history. By comparing the properties of starless and luminous galaxies, astronomers can isolate the effects of stars and feedback, revealing which aspects of a galaxy structure are due to dark matter alone, and which arise from the interplay between stars and gas. Finally, understanding galaxies without stars emphasizes the diversity of the universe. Not all mass forms light. Not all gas collapses into stars. Some structures exist in darkness, coherent and complete, shaped entirely by gravity and the distribution of matter. Starless galaxies demonstrate that the cosmos contains more variety than our senses might suggest. Their discovery provides not only a new type of object to study, but also a deeper understanding of the invisible forces that shape all galaxies. Observing these galaxies strengthens the recognition that the universe is governed as much by unseen presence as by luminous display, and that true comprehension requires looking beyond the light to the structure, motion, and mass that define every cosmic system. Detecting a galaxy without stars requires a shift in perspective. Traditional astronomy relies on light, visible, ultraviolet, or infrared, to reveal the shapes and positions of galaxies. Starless galaxies, however, offer no such signal. They remain invisible to optical telescopes, hiding in the dark reaches of space. Astronomers must look for other signs, ways to trace the presence of mass and structure without relying on light. One of the most powerful methods involves observing neutral hydrogen gas. Hydrogen, the most abundant element in the universe, emits radiation at a specific wavelength of 21 centimeters when its electrons flip spin states. This emission is weak but detectable with sensitive radio telescopes, providing a map of gas distribution and motion across vast distances. By tracing hydrogen, astronomers can locate objects that otherwise leave no trace in visible light. Radio telescopes are the essential tools for this kind of observation. Large arrays combine multiple dishes, each tuned to detect faint signals from hydrogen spread over millions of light years. These instruments produce data in the form of spectra, which reveal both the presence of gas and its velocity along the line of sight. By observing how the frequency of the hydrogen emission shifts due to motion, astronomers can measure rotation within the cloud. A coherent rotation pattern indicates that the gas is bound by gravity, forming a stable structure. These measurements provide the first evidence that the object is a galaxy, rather than a random cloud of interstellar gas, and that its mass is sufficient to maintain cohesion in the absence of stars. Mapping the invisible is not without challenges. The signals from hydrogen are extremely faint, often lost in background noise from the Earth's atmosphere, human-made interference, and cosmic sources. Long observation times are necessary to collect enough data to distinguish real features from random fluctuations. Calibration of the instruments must be precise, and the data require careful analysis to remove artifacts and confirm that the observed patterns are genuine. Even small errors in measurement can lead to incorrect interpretations, so astronomers cross-check results using multiple telescopes and repeat observations over weeks or months. Patience and precision are essential, as the universe reveals these hidden objects slowly and subtly. Gravitational effects provide another method to detect galaxies without stars. The mass of a galaxy, even if invisible, exerts influence on nearby objects. Light from distant galaxies can bend as it passes through the gravitational field of the starless galaxy, a phenomenon known as gravitational lensing. While the effect is subtle for small galaxies, careful measurement of distorted background light can reveal the presence and distribution of mass. Additionally, the motion of neighboring gas clouds or dwarf galaxies can indicate the gravitational pull of unseen matter. By combining these approaches, astronomers obtain independent evidence that the object is not just a cloud of gas, but a galaxy shaped by gravity with a mass comparable to other small galaxies. Confirming the mass and structure of a starless galaxy relies on integrating multiple observations. Rotation curves derived from hydrogen gas provide an estimate of the mass required to sustain the observed motion. These curves show how the velocity of gas changes with distance from the center, and they often reveal that most of the mass lies in an invisible halo, dominated by dark matter. The total mass can then be compared to that of similar luminous galaxies, demonstrating that, despite the absence of stars, the object has sufficient gravity to form a coherent system. In this way, astronomers move from detecting a faint signal to constructing a detailed model of the galaxy's mass distribution and internal dynamics. The spatial distribution of gas also conveys information about the galaxy's structure. In luminous galaxies, stars often define arms, bars, and central bulges. In starless galaxies, gas clouds form the observable structure. Regions of higher density, or clumps, may indicate areas where star formation could have occurred if conditions were suitable. The absence of stars in these clumps emphasizes the contrast between potential and actual formation. By mapping these distributions, astronomers can infer rotation, asymmetries, and even interactions with nearby objects. These subtle features help distinguish a starless galaxy from random gas clouds or tidal debris, confirming that it is a stable, self-contained system. Different wavelengths of observation complement the radio data. While visible light is absent, infrared observations can search for extremely faint stars that might escape detection. X-ray telescopes can reveal hot gas in the surrounding halo or energetic processes, and ultraviolet imaging can check for any trace of young stars. In the case of confirmed starless galaxies, these wavelengths generally detect nothing above the noise, reinforcing the interpretation that stars are entirely absent. By combining these methods, astronomers create a multi-dimensional picture of the object. Mass, motion, gas distribution, and absence of light, all confirming the presence of a starless galaxy. The use of radio interferometry, where signals from multiple dishes are combined to create high-resolution images, allows astronomers to pinpoint the size and shape of the galaxy. These detailed maps show how the gas rotates and how density varies across the system. Small variations in velocity across the cloud provide information about internal turbulence and the gravitational potential. Through careful modeling, astronomers estimate the total mass, the distribution of dark matter, and the galaxy's overall structure. This analysis transforms an invisible cloud into a well-characterized object, providing a clear understanding of its properties despite the absence of visible stars. Observation of starless galaxies also highlights the interplay between environment and visibility. Many of these galaxies are found near clusters or in regions affected by interactions with other galaxies. Stripping of gas, heating by intergalactic plasma, or tidal forces can influence their formation and inhibit star birth. Mapping their position relative to luminous galaxies provides context, revealing how external forces might have contributed to their starless state. By correlating gas maps with known galactic neighbors, astronomers can identify patterns and environmental factors that shape the existence of these hidden systems. Finally, confirming a starless galaxy requires patience and collaboration. Multiple teams often observe the same object with different instruments from different locations on Earth, or even from space. Data are compared, recalibrated, and modeled. Spectra, rotation curves, gas maps, and gravitational effects are analyzed together to construct a comprehensive picture. Each piece of evidence strengthens the conclusion, providing confidence that the galaxy is real, massive, and starless. The process exemplifies the scientific method: observation, verification, modeling, and confirmation. In the end, a starless galaxy is not merely inferred. It is carefully measured, mapped, and understood, despite its complete invisibility in ordinary light. The place where a starless galaxy resides is often as revealing as the galaxy itself. Many are found within larger galaxy clusters, regions where hundreds or thousands of galaxies exist in close proximity. These clusters are filled not only with stars and galaxies, but also with hot, diffuse gas that permeates the space between them. This intergalactic medium can exert forces on smaller galaxies moving through it, stripping gas, heating matter, and influencing the potential for star formation. The environment of a starless galaxy is not empty. It is a dynamic, often turbulent region where gravitational interactions and external pressures shape the fate of the gas within the galaxy. Its surroundings can explain why stars fail to ignite despite the presence of matter. The proximity of other galaxies plays a central role. As galaxies move through clusters, they experience tidal forces from nearby masses, gravitational pulls that can distort shapes and alter internal motion. These forces can stretch and compress gas clouds, sometimes triggering star formation in luminous galaxies. In starless galaxies, however, interactions can have the opposite effect. Gas may be pulled away, dispersed, or heated, preventing it from collapsing into stars. The motion through dense regions of the cluster can strip material through a process known as ram pressure stripping, where the intergalactic medium exerts friction-like forces on the galaxy's gas. Over time, these effects can leave a galaxy intact in terms of mass, but devoid of stars, held together only by the unseen pull of dark matter. Environmental heating is another factor that suppresses star formation. Gas must cool to condense into dense clouds capable of igniting nuclear fusion. In clusters, the surrounding medium is often hot, emitting X-rays and keeping gas temperatures too high for efficient cooling. A starless galaxy immersed in this hot environment cannot form stars because the internal gas cannot lose energy rapidly enough. Even if gas clumps exist, their temperature and pressure prevent collapse. Observations of starless galaxies often reveal a smooth distribution of hydrogen, lacking the dense knots seen in star-forming galaxies. This calm appearance is deceptive, as the galaxy is subject to subtle but persistent forces that shape its evolution in silence. Collisions and near encounters with other galaxies contribute to the picture as well. While massive interactions can trigger bursts of star formation in ordinary galaxies, in smaller systems, the effect can be destructive. Gas clouds may be stripped or scattered, leaving a galaxy with insufficient material to form stars. In some cases, a galaxy may have begun forming stars in its early history, but lost its gas during such an encounter, halting further formation. The starless galaxy, in this sense, becomes a survivor of environmental pressures, its absence of stars a record of its interactions rather than an absence of matter. By studying these locations, astronomers gain insight into the conditions under which star formation is prevented. The density of the local environment also matters. In low-density regions, galaxies can retain their gas more easily, forming stars over billions of years. In high-density clusters, however, the crowded neighborhood introduces constant gravitational influence, leading to stripping, heating, and disruption. Starless galaxies are often found in intermediate or high-density regions, where external forces are strong enough to prevent star formation, but not strong enough to disassemble the galaxy entirely. The balance between external pressure and internal gravitational binding defines the galaxy's survival. Dark matter plays a crucial role here, holding the remaining gas together against tidal and ram pressure forces. The movement of a starless galaxy through its cluster reveals subtle interactions. As it orbits the cluster center, the galaxy experiences changing gravitational fields, varying density of the intergalactic medium, and differing levels of radiation exposure. These factors influence the distribution and temperature of the gas. In some regions, compression may occur, temporarily increasing density without leading to star formation. Elsewhere, stripping may remove gas entirely, creating asymmetries in the galaxy's shape. By mapping the motion and location of starless galaxies relative to their neighbors, astronomers can infer the cumulative environmental effects that have shaped their current form. Observations of the intergalactic medium itself are key to understanding these galaxies. Hot gas in clusters emits X-rays detectable by space telescopes, providing information on density, temperature, and movement. The presence of this medium can explain why hydrogen gas in the starless galaxy remains diffuse and fails to collapse. Additionally, the intergalactic medium can transfer energy through shocks or turbulence as the galaxy moves, subtly stirring the gas without initiating the formation of stars. The combination of gravitational forces and environmental heating creates a situation where matter exists but remains inert, a galaxy in a state of suspended potential. Nearby luminous galaxies can also influence starless systems. Their gravitational fields may draw gas away, or interactions may perturb motion within the starless galaxy, altering rotation and density patterns. In some cases, gas clouds stripped from luminous galaxies can be captured by the starless galaxy, adding to its mass without triggering star formation. These subtle exchanges emphasize the dynamic nature of cluster environments, where galaxies, visible and invisible, interact in complex ways that shape their evolution. A starless galaxy is both affected by and a witness to these processes, its silence telling a story of constant, unseen forces. Even isolated starless galaxies face environmental challenges. While not embedded in clusters, they may exist in regions with diffuse gas or past interactions that removed material early in their history. The absence of nearby galaxies reduces tidal disruption, but the history of the galaxy can still contain moments of stripping or heating that prevented stars from forming. The study of these isolated examples allows astronomers to compare different evolutionary paths, understanding the role of environment versus internal properties in producing starless systems. Each galaxy, whether in a dense cluster or in isolation, reflects the interplay of matter, gravity, and surroundings. The position of a starless galaxy within a cluster often correlates with its size and gas content. Galaxies closer to the cluster center may experience stronger stripping and heating, resulting in smaller, more diffuse systems. Those at the outskirts may retain more gas and exhibit larger volumes, yet still fail to form stars if the gas remains too hot or diffuse. By analyzing the locations and physical properties of multiple starless galaxies within clusters, astronomers can identify patterns that indicate which environmental factors are most influential in suppressing star formation. This approach provides a systematic understanding of how galaxies can exist in darkness within a broader cosmic ecosystem. Environmental factors also include cosmic radiation and feedback from neighboring galaxies. High-energy photons can ionize gas, preventing collapse, while supernova-driven winds from nearby galaxies can stir or heat the intergalactic medium. These influences add layers of complexity, showing that starless galaxies are shaped not only by gravity, but also by energetic processes in their surroundings. Observing these interactions allows astronomers to create models that explain the absence of stars and predict how these galaxies might evolve if conditions change. The environment is thus both the cause and the context for the galaxy's silent existence. Finally, the local environment offers a window into the history of starless galaxies. By examining their surroundings, the distribution of nearby galaxies, the density of intergalactic gas, and the presence of tidal forces, astronomers can reconstruct likely scenarios for how these galaxies arrived at their current state. Each galaxy tells a story of cosmic forces at work over billions of years, of interactions that prevented star formation and preserved gas in a stable, rotating structure. The study of environment is essential to understanding starless galaxies, revealing not only where they exist, but why they remain devoid of stars in a universe filled with light. Galaxies generally form stars through a simple yet delicate process. Gas, primarily hydrogen, collects in dense clouds within the galaxy, pulled together by gravity. As the gas collapses, pressure and temperature increase, eventually reaching the point where nuclear fusion ignites. This birth of a star marks a transformation of raw material into light, heat, and energy, a process repeated across billions of years in the universe. In most galaxies, this cycle continues, producing stars of various ages, colors, and sizes. Stellar, birth, death, and renewal create the luminous systems that dominate visible astronomy. Observing these processes helps astronomers understand the physical conditions that allow matter to transition into stars, revealing patterns of mass, rotation, and chemical enrichment. Starless galaxies disrupt this familiar picture. They possess gas, sometimes in amounts comparable to small luminous galaxies, yet show no evidence of star formation. One possible reason is gas stripping, a process in which interactions with neighboring galaxies or with the hot intergalactic medium remove the material needed to create stars. As the galaxy moves through a cluster, friction with the diffuse plasma exerts pressure on the gas. In strong interactions, significant fractions of hydrogen may be pulled away, leaving the galaxy with insufficient material for collapse. Observations of starless galaxies in dense environments support this idea, as many are located near massive neighbors or within cluster cores, where ram pressure stripping is most effective. The absence of stars may thus reflect a history of gradual or sudden gas loss. Early cosmic events offer another explanation. Galaxies formed during the first billion years of the universe faced intense radiation fields, supernova explosions, and energetic feedback from massive neighboring galaxies. In some cases, these conditions could prevent the gas in a small protogalaxy from cooling and condensing, halting star formation before it ever began. The primordial gas might remain too hot, diffuse, or ionized to collapse. Simulations of early galaxy formation show that small halos with insufficient dark matter mass may struggle to retain gas against heating and cosmic winds. In this scenario, starless galaxies are relics of early cosmic history, structures that assembled gas but never ignited it due to environmental and physical constraints in the young universe. Collisions and near encounters with other galaxies also influence star formation. Unlike dramatic mergers that trigger starbursts, some interactions can disperse or heat gas, leaving a galaxy unable to form stars. A small galaxy passing close to a massive neighbor might lose its gas to tidal forces or be enveloped by the hot halo of the larger galaxy. These encounters can strip material gently or violently, depending on velocity, mass, and angle of approach. The resulting galaxy may remain bound by dark matter, with gas distributed in a smooth, rotating structure, but devoid of the density peaks required for stellar birth. Observations of gas kinematics in starless galaxies show patterns consistent with past interactions, lending support to this hypothesis. Current hypotheses combine these factors into a coherent framework. Many starless galaxies appear in environments where multiple mechanisms could act together. Gas may have been stripped by intergalactic winds, heated by cluster plasma, and disrupted by tidal interactions with nearby galaxies. The result is a system with enough mass to remain gravitationally bound, but without dense gas clouds capable of forming stars. This framework aligns with both observational data and simulations, explaining the presence of gas without the accompanying light. Astronomers use models to test these hypotheses, varying initial conditions such as halo mass, gas density, temperature, and environmental factors to reproduce the observed properties of starless galaxies. Simulations reveal that dark matter is essential for the stability of these galaxies. Without sufficient dark matter, stripped or heated gas would disperse into the intergalactic medium. The dark matter halo acts as a gravitational container, holding the gas in a coherent shape and allowing astronomers to detect rotation patterns. Observations of rotation curves in starless galaxies match predictions from models incorporating dark matter halos, confirming that these invisible structures are central to formation and survival. The gas moves as expected under gravitational influence, even in the absence of stars, demonstrating the halo's stabilizing role. The chemical composition of the gas provides additional clues. Starless galaxies often contain primordial gas, largely hydrogen and helium, with few heavy elements. This suggests that stars never formed in significant numbers, as stellar fusion is the source of heavier elements. In contrast, even small luminous galaxies display enriched gas due to supernova feedback. Comparing gas composition between starless and luminous galaxies allows astronomers to infer the extent of star formation history, or lack thereof, within each system. The data support the idea that starless galaxies are fundamentally different in their internal evolution, not merely missing a few stars, but largely unaltered by the processes that produce visible stellar populations. Observations also highlight the diversity of starless galaxies. Some appear nearly spherical, while others are elongated or irregular, reflecting their formation history and environmental influences. Differences in gas density, rotation speed, and halo mass suggest that multiple pathways can lead to the absence of stars. In some cases, the galaxy may have been stripped gradually, losing gas over time. In others, a single early event may have prevented star formation entirely. Each system provides a snapshot of possible formation mechanisms, allowing astronomers to refine theories and test models against empirical evidence. The role of cosmic timing is significant. A galaxy forming early in a dense cluster might encounter harsh conditions that inhibit star formation, while a similar galaxy forming in isolation may retain its gas and eventually ignite stars. Starless galaxies may represent cases where timing, environment, and initial mass converge to prevent the usual cycle of stellar birth. This perspective emphasizes that starless galaxies are not simply failures, but products of specific cosmic circumstances. Their existence illustrates the delicate balance required for star formation and the variety of outcomes possible in the universe. Current research continues to integrate observational data and simulations. Radio maps, gravitational measurements, and cluster surveys provide a growing catalogue of starless galaxies. By comparing properties across multiple examples, astronomers identify patterns in gas mass, halo structure, and environmental conditions. These patterns inform theoretical models, clarifying which factors are most influential in suppressing stars. Evidence increasingly supports a multi-factor scenario, where gas stripping, early heating, and tidal effects combine to create galaxies that remain dark despite their mass. In all cases, starless galaxies challenge conventional understanding of galaxy formation. They reveal that matter alone is not sufficient. Conditions must allow gas to collapse and ignite stars. By studying these galaxies, astronomers gain insight into the interplay of gravity, gas physics, and environment in shaping cosmic structures. Observing their properties informs broader questions about galaxy evolution, dark matter halos, and the diversity of cosmic systems. Starless galaxies, once theoretical, now stand as empirical evidence that the universe can form coherent structures that shine not with stars, but with the quiet presence of matter and dark matter, waiting for careful observation to reveal their existence. Finally, the study of formation theories emphasizes the unity of observation and simulation. Astronomers observe the gas, measure velocities, map rotation, and analyze location. They then model conditions to replicate these results, testing hypotheses about stripping, heating, and environmental influence. The agreement between data and models strengthens confidence in current explanations, while leaving room for further refinement. Starless galaxies thus provide a laboratory for understanding how galaxies can form in unusual conditions, highlighting both the importance of unseen matter and the subtle interplay of forces that govern the cosmos. These galaxies illustrate that formation is not solely a process of light and stars, but of matter, motion, and gravitational structure, working together to produce systems both visible and hidden across the universe. The discovery of a galaxy without stars reshapes many assumptions about the universe. For decades, astronomers equated galaxies with light. Stars, visible across billions of light years, were the primary markers of structure in the cosmos. They allowed the mapping of clusters, the measurement of mass, and the tracing of cosmic evolution. A starless galaxy forces a reconsideration of this approach. Here is a coherent system with mass, rotation, and structure, yet invisible to optical telescopes. The existence of such galaxies shows that the universe contains more than what can be seen. Light does not define presence, Observing the unseen requires different tools and perspectives, revealing that matter and gravity alone can create coherent structures that persist for billions of years. Dark matter plays a central role in this understanding. Starless. Galaxies are dominated by dark matter halos, which provide the gravitational pull necessary to hold the gas together. Their behavior illustrates the principle that dark matter forms the scaffolding for cosmic structures. Luminous galaxies trace this scaffolding with stars, but the dark matter exists independently. Starless galaxies expose this invisible framework directly, as the gas follows the shape dictated by dark matter without stellar interference. By studying the rotation and distribution of gas, astronomers gain a clearer view of the halo's influence, seeing the shape and strength of the dark matter distribution in its purest form. These galaxies also provide evidence for the concept of dark galaxies, systems rich in mass but devoid of stars. The cosmic web, the vast network of filaments, clusters, and voids that spans the universe, is structured largely by dark matter. Starless galaxies may inhabit these filaments in ways that ordinary galaxies do not, forming nodes of mass invisible to traditional surveys. Their presence suggests that the web contains a wider variety of objects than previously recognized, including systems that contribute to mass and gravitational potential, but remain undetected in visible light. This realization has implications for understanding the total matter content of the universe and how dark matter shapes large-scale structure. The discovery influences models of galaxy formation and evolution. Classical models focus on the collapse of gas in dark matter halos, followed by star formation and subsequent evolution. Starless galaxies reveal that these models must account for scenarios in which gas does not form stars. Simulations now explore conditions under which halos retain gas yet fail to ignite fusion, testing the effects of environment, heating, stripping, and feedback. The results show that a spectrum of outcomes is possible, from fully luminous galaxies to completely starless systems, all dependent on mass, environment, and timing. By integrating these findings, cosmologists refine predictions of galaxy populations across cosmic time. Observational data from starless galaxies provide benchmarks for these models. Rotation curves, gas distribution, and location within clusters all serve as inputs for simulations. The agreement between observed properties and model predictions supports the idea that dark matter dominates formation and structural stability. Starless galaxies act as natural experiments, showing what happens when stars are absent and allowing theorists to isolate the effects of dark matter, gas physics, and environmental forces. In this way, they illuminate processes that remain hidden in luminous galaxies, where stars dominate both light and dynamics. The implications extend to measurements of cosmic mass. Much of the universe's matter is dark, inferred only through gravitational effects. Starless galaxies contribute to the total mass budget of clusters and filaments, influencing the motion of neighboring galaxies and the dynamics of the intergalactic medium. Including these objects in calculations refines estimates of matter density, cluster mass, and the role of dark matter in shaping the large-scale universe. They remind astronomers that visible matter alone does not account for the full story. Unseen structures exert influence just as real as that of luminous galaxies. Cosmological simulations now incorporate the possibility of widespread starless systems. Models of hierarchical structure formation predict that small dark matter halos should exist in abundance, some of which may never form stars. Observing actual examples of starless galaxies validates these predictions and constrains the frequency and properties of such halos. This feedback between theory and observation strengthens confidence in the current understanding of cosmic structure, while also highlighting gaps that remain, particularly regarding the efficiency of star formation and the role of environment across cosmic history. The discovery also raises questions about the evolution of galaxies over time. If some galaxies remain starless, what prevents stars from forming even after billions of years? Are these galaxies permanently dormant? Or could conditions change to ignite delayed star formation? Investigating these possibilities requires long-term observation, monitoring gas density, temperature, and motion, and modeling potential interactions with neighboring galaxies or cosmic filaments. These studies connect the microphysics of gas and dark matter with the macroscopic evolution of galaxies and clusters, providing a bridge between small-scale processes and large-scale cosmology. Starless galaxies also influence understanding of feedback mechanisms. In luminous galaxies, energy from supernovae, stellar winds, and black holes affects gas distribution, heating the interstellar medium and regulating star formation. In a starless galaxy, these processes are absent, allowing astronomers to study a system without stellar feedback. Comparing starless and luminous galaxies highlights the role of these energetic processes in shaping structure, emphasizing that not all galaxies follow the same evolutionary path. The absence of feedback produces a simpler system, governed primarily by gravity and dark matter, yet still subject to environmental influence. Finally, starless galaxies underscore the importance of multi-wavelength observation in cosmology. Light alone cannot reveal the full extent of the universe's structure. Radio, X-ray, infrared, and gravitational studies are essential to detect and understand these hidden systems. Their discovery challenges cosmologists to consider the universe in terms of mass, structure, and motion rather than light alone. Starless galaxies are evidence that the universe is more diverse and complex than early surveys indicated, reminding scientists that unseen matter shapes reality as much as, if not more than, the stars that illuminate it. By mapping and understanding these objects, astronomers gain a clearer, deeper view of the cosmos, its history, and its underlying framework. Observing starless galaxies demands precision, patience, and innovation. Because these systems emit no light, astronomers must rely on indirect methods, particularly radio waves emitted by hydrogen. The faint signal at 21 centimeters is weak, often buried beneath cosmic noise and interference from Earth's atmosphere. Detecting it requires large radio dishes or arrays, sometimes spanning kilometers, working together to increase sensitivity. These instruments collect data over hours or even days, integrating signals to build a clear picture of gas distribution and motion. Even with modern technology, the process is delicate. Small errors in calibration or environmental interference can obscure the already faint signals. Successful detection is therefore a triumph of engineering, patience, and careful observation. Advances in radio astronomy have made the study of starless galaxies possible. Arrays of dishes, linked through interferometry, can create images with high resolution, revealing the structure and rotation of gas clouds. Each dish contributes a piece of the wavefront, allowing astronomers to simulate a single enormous telescope. This technique resolves details of gas motion that would be invisible with a single instrument. Spectroscopy complements imaging, splitting radio signals into precise frequencies to measure velocity shifts caused by rotation. By examining the Doppler effect in hydrogen emissions, scientists can map the movement of gas across the galaxy, calculate mass, and infer the presence and shape of the dark matter halo. These methods transform invisible clouds into measurable, quantifiable systems. Integration of multiple observational methods strengthens the reliability of discoveries. While radio observations detect hydrogen, gravitational effects provide independent confirmation. The bending of light from distant galaxies, though subtle, can reveal the mass of an otherwise invisible system. X-ray telescopes detect hot gas in the surrounding medium, offering context about environmental conditions that might suppress star formation. Infrared instruments search for faint or hidden stars, verifying that the galaxy truly lacks luminous matter. Together, these approaches allow astronomers to construct a multi-dimensional view of starless galaxies, confirming their existence and characterizing their structure with confidence. Relying on a single method would leave room for uncertainty, but combining tools creates a coherent and persuasive picture. Follow-up observations are essential to validate initial detections. A single radio survey may identify a candidate object, but repeated measurements confirm rotation, mass distribution, and gas coherence. Observatories in different locations, observing at slightly different frequencies, help rule out interference or noise artifacts. By comparing results from multiple instruments, astronomers verify that the detected system is not a chance alignment of gas clouds or a spurious signal. These confirmations transform a tentative detection into a fully documented starless galaxy. The process illustrates the rigor of scientific method in astronomy. Observation, replication, and verification before drawing conclusions. Case studies illustrate the power of these techniques. One starless galaxy was initially identified in a wide-field radio survey, appearing as a faint concentration of hydrogen without accompanying light. Detailed follow-up with a radio array revealed rotation consistent with a bound system. Spectroscopy measured velocity, gradients, confirming mass and suggesting the presence of a dark matter halo. Additional observations in X-ray and infrared found no evidence of stars, reinforcing the starless classification. Further modeling indicated that the galaxy's gas had likely been affected by nearby cluster interactions, consistent with theoretical predictions. Such examples demonstrate how observation, analysis, and cross-checking combine to produce reliable knowledge of these hidden systems. Another case involved a candidate in a relatively isolated environment. Radio detection showed a diffuse cloud of hydrogen, moving coherently around a central region. Interferometric imaging revealed slight asymmetries, suggesting past interactions or turbulence. Gravitational analysis indicated sufficient mass to hold the gas together, even in the absence of stars. Follow-up observations over months confirmed the stability of the rotation curve, ruling out chance alignment or transient phenomena. This example emphasizes that starless galaxies are not limited to cluster environments, but can exist wherever conditions inhibit star formation. Observing a variety of cases helps astronomers understand the range of environments and histories that produce these systems. Challenges remain, particularly in identifying faint or distant starless galaxies. The farther the object, the weaker its signal, and the more difficult it is to separate from background noise. Interference from Earth-based radio sources, solar activity, and cosmic phenomena complicates detection. New techniques, such as higher sensitivity arrays, longer observation times, and improved noise reduction, are critical to expanding the catalogue of known starless galaxies. Future observatories will allow deeper surveys, mapping these objects across larger volumes of space and providing a more complete picture of their abundance and properties. Even with modern instruments, interpreting the data requires careful modelling. The rotation of gas can be influenced by turbulence, nearby galaxies, or internal instabilities. Spectroscopic analysis must account for these factors to derive accurate mass and halo estimates. Astronomers use computer simulations to test the plausibility of observed patterns, comparing measured velocity gradients and density distributions with predictions from dark matter models. This iterative process, combining observation and theory, strengthens confidence in conclusions and helps refine techniques for identifying and studying starless galaxies. The integration of observational methods also facilitates discovery in dense clusters. In these environments, gas from multiple galaxies overlaps, and signals can blend, making it difficult to identify individual starless systems. Combining radio data with gravitational measurements and environmental mapping allows astronomers to isolate candidate galaxies and determine whether they are indeed starless or simply faint members of the cluster. This multifaceted approach has proven essential for confirming galaxies that otherwise would remain undetected, hidden within complex environments. Long-term monitoring further enhances understanding. By observing the same galaxy over years, astronomers can detect subtle changes in gas distribution, motion, or interactions with the surrounding medium. These temporal studies reveal dynamics that single observations cannot capture, such as minor disturbances, rotation curve stability, or environmental effects on gas structure. Starless galaxies, though silent in light, speak through these patterns of motion, and careful monitoring allows astronomers to interpret their histories and predict potential future evolution. Finally, observational advances continue to push the boundaries of knowledge. As technology improves, astronomers can detect weaker signals, resolve finer structures, and map larger volumes of space. Techniques developed for starless galaxies are now applied to search for other faint or hidden systems, including low surface brightness galaxies and faint dwarf galaxies. The combination of sensitive radio arrays, spectroscopy, gravitational analysis, and multi-wavelength studies provides a toolkit capable of revealing objects previously invisible. Each successful detection expands our understanding of the universe, showing that light alone does not capture the full diversity of cosmic structures. Starless galaxies occupy a unique place in the cosmos, yet they are part of a broader spectrum of faint and dark objects. Astronomers have long known about low luminosity galaxies, dwarf galaxies, and diffuse systems that barely emit light. These objects often contain some stars but remain faint compared to the bright spirals and ellipticals that dominate the night sky. Starless galaxies, by contrast, have no detectable stars at all. They provide a bridge between truly luminous galaxies and the invisible structures predicted by dark matter simulations. Comparing these systems highlights the continuum of cosmic forms, from bright stellar assemblies to silent gas-filled halos shaped solely by gravity. Some starless galaxies resemble extreme dwarf galaxies in size or gas mass, yet their absence of light sets them apart. Others are more massive, containing enough gas that stars could theoretically form if conditions allowed. Their comparison with low surface brightness galaxies reveals subtle differences. Low surface brightness galaxies often have diffuse stars and faint light, making detection challenging but possible. Starless galaxies, in contrast, emit nothing optically, relying entirely on radio waves and gravitational effects for identification. By studying these relationships, astronomers understand the diversity of galaxy types and how physical processes determine whether stars ignite or remain absent, revealing the delicate balance between gas, gravity, and environment. The prevalence of starless galaxies varies across cosmic regions. In dense galaxy clusters, they are relatively common, suggesting that environmental effects like gas stripping, tidal forces, and heating suppress star formation. In these regions, gas-rich halos may survive without forming stars, held together by dark matter and surrounded by the hot intracluster medium. In less crowded areas, starless galaxies are rarer, as isolated halos often retain gas long enough to ignite stellar formation. Observational surveys indicate that the population of these galaxies is significant, but still much smaller than the population of luminous galaxies. Their distribution reflects both cosmic structure and the influence of environment on galaxy evolution. Mapping their locations provides insight into the cosmic web. Starless galaxies often trace the same large-scale filaments and cluster outskirts as luminous galaxies. Their positions reveal the underlying dark matter scaffolding, independent of stars. By observing patterns of gas in these systems, astronomers can infer connections between dark matter filaments and luminous matter, revealing the unseen skeleton of the universe. This perspective shows that visible light captures only a portion of cosmic structure, while dark or faint systems, including starless galaxies, illuminate the broader architecture of the cosmos. Future surveys will be shaped by the need to detect these hidden systems. Large radio arrays, such as the Square Kilometre Array, will provide unprecedented sensitivity to neutral hydrogen across vast volumes of space. By surveying wide regions with high resolution, astronomers can uncover faint or distant starless galaxies that current instruments cannot detect. Complementary observations in other wavelengths, such as X-ray and infrared, will rule out faint stars and examine environmental influences. These surveys promise to expand the catalogue of starless galaxies, revealing how common they are and how they fit into models of galaxy formation across cosmic history. Space telescopes also contribute to this effort. While optical telescopes cannot detect starless galaxies directly, they provide context by mapping surrounding structures, nearby luminous galaxies, and diffuse clusters. Infrared instruments can detect any faint or obscured stars that might escape optical surveys, confirming the starless nature of candidates. X-ray observatories reveal the state of the intergalactic medium and cluster gas, showing how environmental heating and turbulence influence galaxy evolution. By integrating data from ground-based and space-based instruments, astronomers can construct a multi-layered picture of these elusive systems and their surroundings. The study of starless galaxies informs predictions for other dark or faint objects. Many theoretical models suggest that small dark matter halos exist throughout the universe, some of which may never form stars. Starless galaxies represent observable examples of these halos, confirming that mass exists in forms invisible to light-based surveys. Understanding their properties helps refine expectations for the abundance of low-mass, non-luminous halos, providing insight into the full spectrum of cosmic structures. Observing these systems bridges the gap between theory and reality, showing that dark matter halos produce real measurable objects even without stars. Comparing starless galaxies with satellite galaxies of larger systems also highlights differences. Satellites often retain stars despite environmental stripping, suggesting that mass, halo depth, and gas density influence whether star formation continues. Starless galaxies may occupy smaller or more fragile halos, where external effects prevent stars from forming entirely. This comparison emphasizes that stellar absence is not simply a random occurrence, but the result of specific physical conditions. By analyzing both starless and faintly luminous galaxies, astronomers can determine the thresholds that govern stellar birth, dark matter dominance, and survival in different cosmic environments. These systems also influence the planning of future instruments. Knowing that galaxies exist without stars encourages the development of high-sensitivity, wide-field radio surveys capable of detecting neutral hydrogen across immense volumes. Instrument design now accounts for faint, diffuse signals, long observation times, and careful noise suppression. Computational techniques for combining multiple observations and filtering interference are equally important, as they allow astronomers to extract signals from the background. The discovery of starless galaxies demonstrates that the universe contains structures invisible to traditional surveys, motivating new approaches to detect and study them. Finally, starless galaxies remind scientists that the universe is more complex than visible light alone suggests. They are part of a continuum of faint, dark, and hidden objects that challenge assumptions about the prevalence of stars and the interpretation of cosmic maps. Observing them refines knowledge of galaxy populations, dark matter halos, and the structure of clusters and filaments. Future surveys, combining radio, gravitational, and multi-wavelength observations, will uncover more of these systems, expanding understanding of cosmic diversity. Starless galaxies, silent yet present, illustrate the hidden richness of the universe, revealing structures that must be accounted for to fully grasp the scope and complexity of the cosmos. The discovery of starless galaxies has shifted the focus of astronomical research in subtle but profound ways. Astronomers now recognize that light alone does not define the universe, and that structures can exist entirely unseen, without altering gravitational dynamics. Ongoing studies aim to explore these hidden systems systematically, mapping their distribution, mass, and interaction with the cosmic web. Researchers refine techniques for detecting faint hydrogen emissions, often combining long-duration radio observations with gravitational lensing measurements and environmental analysis. Each detection adds to the growing catalogue, providing data that inform theories of galaxy formation, evolution, and dark matter structure. Observing starless galaxies requires patience, but the insights gained illuminate aspects of the universe that were previously invisible, reshaping models and expectations across cosmology. Current research projects focus on expanding surveys to cover more of the sky, reaching both dense clusters and isolated regions. Arrays of radio telescopes operate in coordinated networks, allowing for high-resolution mapping of neutral hydrogen in distant systems. These observations track the motion and density of gas, revealing rotation curves and the presence of dark matter halos. When combined with optical, infrared, and X-ray data, astronomers can determine whether a galaxy is truly starless or contains faint stars below current detection limits. Cross-checking across multiple instruments reduces errors and confirms the nature of these elusive objects. In this way, starless galaxies are studied with unprecedented rigor, bridging the gap between theory, observation, and simulation. The discovery also encourages the development of new instruments. Radio arrays are becoming more sensitive, with larger collecting areas and wider baselines to detect fainter emissions. Future facilities, such as the Square Kilometre Array, promise to identify vast numbers of starless galaxies, including those at greater distances than previously observable. Innovations in signal processing and noise reduction improve the ability to isolate weak hydrogen lines from background interference. Spectroscopic instruments are designed to measure velocities with extreme precision, enabling astronomers to calculate mass and dynamics accurately. Together, these tools expand the capacity to find hidden galaxies across the universe, revealing structures that were once entirely speculative. Space-based missions complement ground observations. While optical telescopes cannot see starless galaxies directly, they provide crucial context by mapping surrounding luminous galaxies and the large-scale structure of clusters and filaments. Infrared instruments detect any faint, hidden stellar populations, confirming the absence of light, where radio signals indicate the presence of gas. X-ray telescopes measure the temperature and density of the intergalactic medium, showing how environmental factors influence star formation. By integrating these datasets, astronomers construct a three-dimensional picture of starless galaxies, their surroundings, and the physical forces that shape their evolution. Each observation layer adds clarity to the hidden universe. The study of starless galaxies informs theoretical research as well. Simulations now include scenarios in which dark matter halos contain gas but never form. Stars, testing the effects of halo mass, environmental heating, and tidal interactions. By comparing these models with observations, astronomers refine understanding of the physical thresholds required for star formation. Starless galaxies become benchmarks for testing predictions, illustrating how gravity, gas dynamics, and environment interact to produce diverse outcomes. The more these systems are observed, the better models can account for the full range of galactic behavior, from bright spirals to completely invisible halos. These galaxies also reshape the philosophy of cosmic observation. For centuries, astronomy relied on light, from the earliest telescopes to modern optical surveys. Starless galaxies remind scientists that the universe cannot be fully understood through light alone. They highlight the unseen scaffolding of dark matter and the subtle dynamics of gas in the absence of stars. Philosophically, this challenges perceptions of what is real in the cosmos. A galaxy can exist, exert gravitational influence, and occupy space without producing a single photon of visible light. It is a silent, invisible presence, demanding a reconsideration of what counts as an observable object in the universe. The implications extend to cosmic evolution. Starless galaxies provide evidence that not all halos successfully produce stars, demonstrating that the processes of star formation are not inevitable. Environmental factors, gas physics, and cosmic timing can prevent the ignition of nuclear fusion, leaving matter dormant in structured systems. Observing these galaxies offers a rare glimpse into conditions that diverge from the common path of luminous evolution. They serve as natural laboratories, showing what happens when matter and gravity interact without the influence of stars, energy feedback, or radiation pressure. Each galaxy reveals a story of potential that was never realized, captured silently in hydrogen clouds bound by dark matter. Future missions are planned to capitalize on these insights. Radio telescopes with greater sensitivity and resolution will survey larger volumes of space, targeting regions where dark matter halos are predicted to exist. Multi-wavelength campaigns integrate optical, infrared, and X-ray data to fully characterize the environment. Some proposals involve space-based radio observatories to avoid Earth-based interference, allowing for cleaner detection of weak signals. These missions aim not only to find additional starless galaxies, but to measure their properties precisely, from mass and rotation to gas density and halo structure. The data will guide models of galaxy evolution and provide empirical constraints on the abundance of dark halos in the universe. The practical benefits of studying starless galaxies extend to understanding other cosmic phenomena. Low luminosity and dark objects are difficult to detect, yet they influence galaxy clusters, gravitational lensing patterns, and the motion of nearby galaxies. By quantifying the mass and distribution of starless galaxies, astronomers can refine estimates of cluster mass, dark matter density, and the dynamics of cosmic filaments. This contributes to a more accurate map of the universe, revealing structures that cannot be traced by stars alone. Starless galaxies act as signposts of dark matter and as benchmarks for cosmic mass distribution, bridging the gap between theory and observation. The ongoing exploration of starless galaxies also emphasizes the collaborative nature of modern astronomy. Observations require coordinated networks of telescopes, long-term monitoring, and data sharing across institutions worldwide. Combining expertise in radio astronomy, gravitational analysis, simulation, and multi-wavelength observation enables scientists to interpret subtle signals reliably. The discovery and study of these galaxies illustrate how scientific progress depends on collaboration, technology, and the integration of multiple perspectives to understand phenomena beyond the reach of traditional methods. In the end, starless galaxies embody both scientific and philosophical significance. They reveal the limits of perception and the necessity of looking beyond light to understand cosmic structure. They challenge assumptions about galaxy formation, showing that not all dark matter halos produce stars. They provide laboratories for studying gas dynamics, environmental effects, and dark matter in isolation. They illustrate the power of careful observation, innovation, and theoretical modeling in uncovering hidden aspects of the universe. Each new discovery expands knowledge, suggesting that even in apparent emptiness, the universe contains complexity, structure, and history waiting to be revealed. As research progresses, starless galaxies will continue to influence the priorities of astronomy. Their study informs the design of telescopes, surveys, and simulations, guiding scientists to seek the unseen and consider the full range of galactic possibilities. They demonstrate that the universe is not fully captured by visible light, and that truly invisible systems exist in abundance. By exploring these galaxies, astronomers gain insight into the hidden scaffolding of the cosmos, the physics of gas and dark matter, and the diverse outcomes of galaxy formation. The discovery of starless galaxies stands as a reminder that the universe contains more than what can be seen, and that patience, ingenuity, and careful observation can reveal worlds that were once entirely hidden from view. Ultimately, these galaxies invite reflection on the nature of observation itself. They occupy space, possess mass, and interact gravitationally, yet remain invisible to traditional surveys. They prompt a rethinking of how reality is defined in the cosmos, emphasizing that existence does not require light. Scientific inquiry expands as instruments, methods, and perspectives evolve, uncovering structures that were once theoretical. Starless galaxies, though quiet and dark, contribute to the story of the universe, reminding humanity that even in darkness, matter and structure endure. They are both objects of study and symbols of the unseen, a testament to the depth and complexity of the cosmos. By continuing to search, measure, and understand, astronomers reveal the richness of the universe in all its luminous and invisible forms.